Hello! So you want to understand chemistry. That's awesome. Chemistry is not just about weird smells and explosions in a lab, it's the science of stuff. The phone in your hand, the air you're breathing. Think of atoms as the ultimate Lego bricks of the universe. Everything you can see, touch, imagine. Understanding them is the first most important step to understanding everything else. It's a journey that starts small but explains the biggest things in the cosmos. So, what's an atom made of? It's not just one solid little ball, the nucleus, super dense central core, protons, neutrons. Protons have a positive electrical charge, neutrons have no charge, they're neutral. Electrons zooming in a cloudy region around the nucleus. If atoms are the letters of the chemical alphabet, then the periodic table is the dictionary. It's one of the most powerful tools in all of science. It's not just a random chart of elements, it's a beautifully organized map that tells us a huge amount about each element's properties. It arranges all the known elements in order of their atomic number, that is, the number of protons they have. But its real genius is in its columns and rows. Learning to read the periodic table is like getting a superpower for predicting chemical reactions. The rows of the periodic table are called periods. Move left to right across a period, and each element gains one proton and one electron. This shows a gradual change in properties. The columns are called groups or families. Elements in the same group have the same number of electrons in their outermost shell. These are valence electrons, and they drive chemical bonding. For example, everything in the first column, lithium and sodium, has one valence electron and reacts similarly. Atoms, for the most part, don't like to be alone. They like to hang out with other atoms. The forces that hold atoms together are called chemical bonds. The whole goal for most atoms is to become stable. Stability usually means having a full outer shell of electrons, like noble gases. To achieve this stable state, atoms will give away electrons. To achieve this stable state, atoms will take electrons. To achieve this stable state, atoms will share electrons. This process creates molecules and compounds, like water, H2O, table salt, nickel, complex proteins in our bodies. There are three main types of chemical bonds: ionic, covalent, metallic. A simple diagram illustrating the three types of chemical bonds: ionic, electron transfer; covalent, electron sharing; and metallic, electron C. The type of bond depends on the elements and their valence electrons. It's all about electronegativity, how strongly an atom pulls electrons. If there's a big difference in electronegativity, one might snatch an electron. If they are similar, they might share electrons instead. Ionic bonds are the drama of the chemical world. They form between atoms that have very different electronegativity values. Typically, this happens between a metal and a non-metal. Metals found on the left side of the periodic table have just one valence electron, have two valence electrons that they are more than happy to give away. Non-metals on the right side are just a few electrons short of a full shell and desperately want to gain them. It's a perfect match. The metal atom transfers one or more of its electrons to the non-metal atom. It's a complete giveaway, not a sharing arrangement. When an atom loses an electron, it becomes a positively charged ion, called a cation. This makes sense because it now has more positive protons than negative electrons. The atom that gains the electron becomes a negatively charged ion, called an anion. Unlike the give and take of ionic bonds, covalent bonds are all about cooperation and sharing. These bonds typically form between two non-metal atoms that have similar high electronegativity values. Neither atom is strong enough to completely pull electrons away from the other. So instead of one atom winning and one losing, they reach a compromise. They share one or more pairs of valence electrons. These shared electrons then orbit the nuclei of both atoms, effectively holding them together in a stable unit called a molecule. This is the bond that forms things like water, carbon dioxide, organic molecules that make up life. Let's look at a simple example: a hydrogen molecule. A single hydrogen atom has one proton and one electron. It wants two electrons to fill its first electron shell and become stable. When two hydrogen atoms get close, they each share their single electron with the other. Now, each hydrogen atom gets to feel like it has two electrons, making both stable. That shared pair forms a single covalent bond holding the two hydrogen atoms together. Now that we know how atoms bond, we can start looking at chemical reactions. But how do we know how much of one substance will react with another? We can't just throw things together and hope for the best. That's where stoichiometry comes in. It sounds like a complicated word, but it's really just the chemistry version of following a recipe. Stoichiometry allows us to calculate the amounts of reactants, the starting ingredients, products, the final stuff in a chemical reaction. It's all based on the law of conservation of mass. Matter cannot be created or destroyed. The first step is a balanced chemical equation. A chemical equation is like a recipe, showing reactants on the left and products on the right, separated by an arrow. For example, the formation of water. 2H2 plus O2 gives 2H2O. So chemists use a special unit called the mole, a very, very big number, 6.022 times 10 to the 23rd. Chemical reactions don't just transform matter, they also involve energy, usually in the form of heat. Thermochemistry is the study of the heat energy associated with chemical reactions and physical changes. Some reactions release heat into their surroundings, making things feel hot. These are called exothermic reactions. Think about a burning log in a fireplace. The combustion of wood releases heat and light. Other reactions need to absorb heat from their surroundings to happen, making things feel cold. These are called endothermic reactions. A chemical cold pack is a great example. Mixing the chemicals inside absorbs heat from your skin. The total energy of a system is complex, but in chemistry we focus on a property called enthalpy. H. Enthalpy measures the total heat content of a system. We can't measure absolute enthalpy directly, but we can measure the change in enthalpy, delta H or dH, during a reaction. dH tells us how much heat is released or absorbed. We've talked about what stuff is made of and how it reacts, but what about the different forms it can take? Matter generally exists in one of three states: solid, liquid, gas. The state depends on two competing factors: intermolecular forces, the attractions between particles, kinetic energy of the particles, how much they're moving. Kinetic energy is directly related to temperature. When temperature is low, kinetic energy is low, so intermolecular forces can hold particles tightly together. When temperature is high, kinetic energy is high, so particles can overcome those forces. Let's start with solids. In a solid, the particles have low kinetic energy. Strong intermolecular forces lock particles into a fixed, rigid structure. Particles can't move freely, they only vibrate in place. So far, we've used a pretty simple model of the atom with electrons orbiting the nucleus like tiny planets. This is a helpful picture, but it's not the whole story. The reality is much, much weirder. Welcome to the world of quantum mechanics. At the incredibly small scale of atoms and electrons, the normal rules of physics that we see in our everyday lives break down. Quantum theory is the set of rules that governs this bizarre microscopic realm. One of the key ideas is that we can't know both the exact position and the exact momentum of an electron at the same time. This is the Heisenberg uncertainty principle. Because of this uncertainty, we can't think of an electron as a tiny ball following a neat, predictable path. Instead, we have to describe its location in terms of probability. We talk about orbitals, which are not orbits, but rather three-dimensional regions of space around the nucleus where there is a high probability of finding an electron. Different atomic orbitals, showing the spherical s orbital and the dumbbell-shaped p orbitals. So we've taken a whirlwind tour of general chemistry, from the tiniest atoms to the weirdness of quantum mechanics. We've seen how atoms are built, how they are organized in the periodic table, and how they bond together to form everything around us. We've learned how to follow a chemical recipe using stoichiometry, how energy flows in reactions with thermochemistry, and why stuff exists as solids, liquids, gases. But they are all deeply interconnected, painting a complete picture of the material world. Because chemistry is the central science. It's the bridge that connects the fundamental physics of particles to the complex, large-scale systems of biology. For engineers, the story is the same. If you're a materials engineer, you're using chemistry to design stronger materials, and the key to solving some of the biggest challenges facing our planet, developing new energy sources, curing diseases.